because this tester told me that a capacitor was a resistor, I decided to make my circuit that I published a few days ago. And that was this circuit, a capacitor tester in a more or less definite way. And for everyone who wants to build this circuit again, also make the circuit, I've made this drawing, and I hope it's visible. Very simple circuit, and let's look more closely to that circuit. At the moment it's supplied with 17 volts, and of course I have used a 7812 voltage stabilizer, because when you want to do measurements, the voltage of a measurement circuit must always stay the same. So here we have a stabilized voltage of 12 volts, and here that's 7812 stabilizer unit, and the series resistor of 330 ohms, 1 watt, perhaps 0.5 watt also will do, no problem, and 2 capacitors connected to that 7812 voltage stabilizer. Input now 18 volts or 70 volts or 20 volts, but always 12 volt out. And that means that the circuit is usable for measurements. When you look at the first circuit that I made, there was a potentiometer here, but now I've used fixed value resistors. The voltage divider consists of 200k resistors, together in series 200k and 47k, and on that node where the wiper was originally, we hook up 200k resistors to the base of the first transistor and the base of the second transistor. And furthermore, it's very simple. There's one 10 nanofarad capacitor going from the collector to the base. Collector first transistor, base second transistor, and the measurement unit is here. And I've soldered a capacitor of 10 picofarad parallel to the probes, and that means that we always have a frequency of, say, 16 kilohertz. Sorry, 1.7 kilohertz. So 1700 hertz approximately. Anyway, because of that plate, you can easily take the capacitor up, put it on the 2 electrodes, and then look at the scope. So let's do that for a 0.22 microfarad, so 220 nanofarad capacitor. The scope is here. The frequency changes to of course to a very low value, and we reach 63 Hertz. Let's take another capacitor. Let's take this capacitor of 0.22 microfarad. Another brand, but of course it must be approximately on the same frequency. And here we reach 73 Hertz. Okay, there are of course tolerances. That's always clear. By the way, you see that 7812 stabilizer unit. This is a capacitor of, say, I think 47 nanofarad. I put it down here. We see the frequency. The trigger of my scope is not connected properly anyway. 188 Hertz. And now we take this capacitor, the same brand, put it on the electrodes, going from 70 kilohertz to 188 Hertz. And I've made this contact surface by purpose in this way, because you can also test capacitors like this. And you can easily push them on these two electrodes. And this capacitor shows 61 Hertz. And it is 0.27 microfarad, so 270 nanofarad. Let's go to 1 microfarad and see what happens when we connect it to our probes. I hope it will succeed. Yes, it succeeds. A very low frequency, 19 or 20 Hertz. So the whole circuit is, in my opinion, very useful. I made it by purpose in this way, on a piece of wood, well varnished, with this type of glue. There are more videos on my YouTube channel. It acts as a kind of shellac, and that makes that all the connections here between the brass pins have a very low inductance. Perhaps when you make such a circuit on in another way, it could be that it doesn't work. There's no guarantee. But when you make it in this way, it will surely work, because of the low inductance, the low capacitance between all the pins on the breadboard. It's a kind of way of making circuits between experimental and definite. And in my opinion, that's a good way. You can develop your circuits experimentally, etc. By the way, of course, it's possible to develop this circuit on a printed circuit board. No problem at all.